Welcome back to Mathematics Lifeline. In today's video, I want to show you an integral that can only be solved using probability and statistical techniques, and it cannot be solved using any sort of calculus integration technique. So this question actually appeared on a qualifying exam, a PhD qualifying exam, and we just want to find the numerical value of this integral, which we can do, but not by using calculus. So let's go ahead and talk about the solution here. So we need to delve into the world of statistics and probability. So when we write the solution down, again, this is something that you may not immediately think of, but we're going to define a bunch of statistics. So we're going to say let x1, x2, up to xn be exponential random variables with parameter 1. Okay, and then we're going to define this term y sub n. We're going to set it equal to x1 plus x2 plus all the way to xn. Now this is the same thing as the series from I equals 1 to n of xi. Now what I'm about to tell you can be derived using moment generating functions, but we're not going to do that in this video. What's important right now, and we'll just treat it as a fact, is that the sum of these exponential random variables or statistics can be actually rewritten as a gamma distribution. So when we have n exponential terms with parameter 1, the sum of them will follow a gamma distribution with parameters n and 1. Okay, and that's going to be really important because we're going to need to use that distribution function to do this integral. So we know now that y sub n is n of these statistics summed together. So we can actually try to start using the central limit theorem because we know that as n gets larger, this sum can be standardized. It can be standardized to approach the standard normal distribution. So when we standardize y sub n, we want to look at what the mean and the standard deviation are. So we know that the expected value, or the mean of y sub n, that's going to be n, and it's actually the same thing as the variance. Variance is going to also be n. So that means that the standard deviation, which I'll write as SD, is the square root of n. And remember that whenever we standardize a random variable, we need to take the variable, we need to subtract its mean, so we're going to subtract n, and then we divide by the standard deviation. So we divide by the square root of n in this case. So let's look instead at the limit as n goes to infinity of the probability that the standardized random variable, so y sub n minus n over square root n, is less than or equal to 0. Okay, so we can do this, and then we can actually apply the central limit theorem. Because as n goes to infinity, this approaches z. So this is going to be the probability that z, which is the standard normal random variable, is less than or equal to 0. But we know that with the normal distribution, especially the standard normal distribution, right, this has this bell curve shape, which I'll extend this. Now this mean right here is at 0, right? So when we look at the area to the left, so all of this area, that's 1/2 of the curve because the standard normal distribution is symmetric about 0. So the probability that our z value is left of 0 or less than or equal to it is equal to exactly 1/2. Okay, so now we have kind of a guess of what this integral can evaluate to, but we need to show that this is the same thing as the integral right here. So let's examine this probability. So the probability that y sub n minus n over root n is less than or equal to 0, well, let's go ahead and just solve for y sub n on the left side. So what we can do is multiply by square root n on both sides, which when we multiply by 0, it'll just go away. So y sub n minus n is less than or equal to 0. And then we'll just add the n to both sides. So this is equal to the probability that y sub n is less than or equal to n. Okay? But now, remember how we define cumulative distribution functions, right? When we have something with this less than or equal to, this can be defined in terms of the integral from 0 to whatever we're integrating over, right? We're going to define it as the integral from 0 to n, right, of the PDF function, of the probability density function. So when we're looking at this gamma distribution, we just need to integrate its probability density function from 0 to n. Now, when we look at a gamma distribution with parameters n and 1, the PDF is going to be e to the minus t, t to the n minus 1, over n minus 1 factorial. And then we'll integrate that with respect to t, and that is exactly this integral right here. So that limit as n goes to infinity, we used to use the central limit theorem, but we actually end up showing that this will end up turning into the exact same integral. So we know, because of what we just did, that this integral will evaluate to 1/2. So yeah, this is a very interesting question because calculus doesn't solve this. You have to go into statistics, and even then it's not really that long of a solution, right? We were able to use the central limit theorem once we standardized the variable, and at that point, it's pretty simple to see that the area left of 0 is 1/2 if you know anything about the normal distribution. So yeah, I hope you enjoyed this video. This is a very complicated problem. Again, it was on a PhD qualifying exam, but I think it's very interesting, and the person who created this was very clever in doing this, and also kind of mean to the students. But anyway, I hope you enjoyed, and if you have any questions, feel free to let me know. But if not, I will see you in the next video. Thanks for watching.